Yeah, so now after loading the dataset, the next logical step is to prepare the training set batches that we will use in the data loader when we are training the LLM. So here is just a brief overview again, where we have all the 9 steps in this section. We are at step 2, and then later we will load these batches into the data loaders. It looks like it's a small step in the grand scheme of things, but it is, I would say, the most crucial aspect when instruction fine-tuning an LLM, because everything down here, like loading the pre-trained LLM, instruction fine-tuning the LLM, we get to reuse functions from chapter 5, because the instruction fine-tuning is still training the LLM to predict the next token in the dataset. So here it's really important that we set up the dataset correctly so that the model can actually learn like we want it to learn. And so it looks like a small section, but there are quite a few steps involved. Like I mentioned, one of the most crucial sections here. So we have 5 steps that we will implement in the data set setup. So we have step 1, formatting the data. So essentially applying this format function that we developed to convert the JSON entries into this text. Then we will use the tick token tokenizer to turn the text into token IDs. Then we will be padding the data set to the longest sequence. We will apply this here on a batch basis. In chapter 6, we padded it based on the longest example in the dataset. We will be a bit more efficient here, and we will pad only to the longest element in each batch, because it's a bit excessive if we would batch it or pad it to the longest example in the training set. We will have a excessive amount of padding tokens, and to avoid that, we will apply the padding on an individual batch basis. For example, this could mean that one batch has the longest example consisting of 80 tokens, one could have 1000 tokens, like another batch could have 500 tokens, and so forth. But we will get to this when we implement this. So the idea here, or the step is, we have the input token IDs, and then we are padding them to the longest element in the batch. And input token IDs here means this whole input text. So I realize it might be confusing because it contains the response here, but it's similar to chapter 5, where we are interested in training the LLM on the next token. Later, when we get to use the LLM on new data, this will only include the boilerplate here and the instruction input. It will not include the response. The response is only necessary, of course, during training, because that's what we want the model to learn. So in this context, input IDs means everything up here. And so we have the input IDs here. And the next step would be creating the target token IDs for training. So the target token IDs are the input token IDs shifted by 1 position. Again, similar to chapter 5. So if our input token IDs are 318, 281, 12,064, our target token IDs are 318, 281, 12,064. You can see these 3 are here basically. So we are shifting it by 1 position. That means we are removing this first token here. And to make the input IDs and the target IDs the same length, we add an additional padding token ID. This is why you only see 3 here, 3 padding tokens, and here are 4, because yeah, we have to, if we remove 1 token here at the front, we have to add 1 more token to have the same length again. And yeah, but the concept here is the same as in chapter 5, that it is shifted by 1 position. A new concept here compared to, let's say, chapter 6, when we do padding, is that we, at the end here in step 5, we are replacing this excessive padding amount by mask tokens here, -100. And this will help us to ignore padding tokens during training. So padding tokens are used to make everything the same size so that we can create these nice tensors for training. But we don't want the model really to learn based on how many padding tokens we have. Because imagine we have an example. If it ends up in a batch where the longest example is 1000 and our example is 100, we have 900 padding tokens. And then it might influence the loss function. And compared to a different batch where there are only fewer padding tokens. So we don't really want to make our loss or anything dependent on how much padding we have. So by replacing these by these so-called mask tokens, we can ignore those in the loss. So the loss will not let's say, consider those when creating when computing the cross entropy loss. But we will get to that later in the section. So here I just wanted to briefly outline the steps that we are going to take. So formatting the prompt template, tokenizing, then adding padding tokens, creating the target IDs, and then masking the excessive padding tokens at the end. By the way, we will keep one padding token here because we want our model to generate a response with a definitive ending. So pre-trained models, they always keep on generating more text if we let them. Here, we want the model to generate an end of text token, this padding token, 50,256, if the model is finished with the response. And so this will also allow us to be more efficient so that the model, that we don't have to iterate a max number of tokens, and then we know exactly when the model is finished. So one padding token is always kept. But we will get to that when we look at the code here. So let's start with the instruction data set that we will set up. So one more figure I wanted to show you. So here we have these 5 steps, 1 to 5, and we will be first coding steps 2.1 and 2.2. So these first steps, where the first steps include applying the prompt formatting template and then converting them to token IDs. So essentially going from this JSON format entry into the text and then creating the token IDs. So let's code this up. So for that, we will create an instruction dataset, and this instruction dataset uses the dataset class. It inherits from the dataset class, similar to what we have done in chapter 2 and chapter 6. And here, we just assign the dataset. The dataset here is the JSON dataset. We have a list. The list will keep collecting our token IDs for each entry. So if we have 1,000 training entries, this will be a list of 1,000 token ID lists. And so what we are doing is we are applying our familiar format input function. That is the function we used before on the entry that we iterate over. So that will create this format here in the center. So we are going from entry to this formatted entry. Next, we will also add the response text. So this is the response that we add to the input. And then we will encode this. So the encoding here means that we go from text into token IDs. Okay, so this is what we are doing. We are collecting them in the encoded texts. And then here, the length function will give us the length of the data set. Whether we call length on data or encoded text, it doesn't matter. It just gives us the length, which the data loader requires for the shuffling and so forth. And here the get item will return one item from our encoded text at a time. And so this is something that is used by the data loader to build the batches, similar to chapter 5 and 6. So yeah, this is our instruction data set here. Oops. And so this one will be based on the tick token tokenizer. So let me just, so that I don't forget this later, let me just import this. Oops. Tick token. And then we will have tokenizer.get encoding GPT-2. Sorry, I made a mistake. This should be, oops, tokenizer equals tick token get encoding. Okay, so this is our tokenizer, and that is going to be used here. Now we have completed steps 2.1 and 2.2. And next we will create a collate function. So what is the collate function? First, this is just a draft. I call it draft 1 because we are going to refine it. But this is a function that will operate on each batch that the data loader generates. So later we will have the data loader like before, when we create our, let's say, train loader. And the data loader will accept the training data set, which will be based on our instruction data set. And in addition, we will also provide a collate function. So here we would, for example, provide this one. And this will do certain operations on each batch, because right now we only implemented steps 1 and 2.2. Next, we want to take care of steps to 3, to 4, and to 5. And like I mentioned, we only want to apply the padding on a batch basis so that each batch is independent of the other batches, so that we don't have this excessive amount of padding tokens and so forth. And so the collate function will take care of steps 2.3, 2.4, and 2.5. Our first draft here, draft version 1, this is a very simple one. This will only do the padding here. So this will only do step 2.3. I will modify it shortly to also do step 2.4 and 2.5, but stay tuned for that. Let's do one thing at a time. So in that case, we won't technically use it like this. We will use a different collate function later. So let me just also comment this out so it's not too confusing. So how does the collate function work, this particular one? So here it receives a batch. This batch is created by the DataLoader, by the way, so we'll get to the DataLoader later. We will work with the collate function here in isolation, and we'll also test it in isolation, and later we will test it again with the DataLoader. But conceptually, this receives an input batch. We define what token ID we want for the padding, and then what device the data is supposed to be on. And here we determine the longest item in the batch. This is similar to what we have done in chapter 6. In chapter 6, we did that for the whole data set. Here we do it for each item only in the batch. We have an input list here, and the list will collect our padded inputs. So here encoded text collected our tokenized inputs. This is similar, but now we will have these padded inputs. So before we had just the regular token IDs. Now we will have the padded token IDs that we will collect here. And yeah, maybe you can pause and look through this. There might be different ways you can implement this. This is my way how I implemented this essentially. So maybe before I explain all the details why the +1 and the -1. So this is just one way I found that worked, because I did some experiments and I had sometimes an extra padding token or was missing a padding token. And with this implementation, I made sure that I always have the right amount of padding, where the padding is also determined here essentially by the difference between the longest element in the batch and then the actual length of that item, similar to what we have done in chapter 6. So when we add the padding token IDs, and then we keep adding the padding token IDs to our input list. So, and then at the end, we stack those. So because these are just lists, but the DataLoader expects batches, right? So the DataLoader passes a batch to this one that is in a tensor format, and it also expects as output a tensor. So here we are stacking those lists as a tensor. We are essentially just converting them into a tensor and then also putting them on the target device that we can choose, CPU, GPU, for example. But yeah, so maybe a lot of code here. If it's confusing, let us just test this in isolation. I mentioned in the next sections, we will be plugging this into the DataLoader, but it's not a bad idea to test this before we get to the next stage. So I hope also, by the way, it's not too loud in terms of background noise. There's really a big thunderstorm outside, so hope I don't lose power. We'll see. So here we are testing now this collate function in isolation on some inputs. So we have an input consisting of 5 tokens, 2 tokens, and 3 tokens. And ideally, what we want this to do is we want this to so by the way, let's also just assemble this as a batch here. We want to assemble this in a way that we have the correct amount of padding for each of these items. And this will be determined by the longest element here. So ideally, we want to see that this will have 3 padding tokens. So they're not X, they will be token ID 50,256. And by the way, where you, if you're wondering what these token IDs here mean, I just made up some numbers from 0 to 9, just so that it is a bit visually easier to read. Of course, these would be, in reality, when we apply it to our DataLoader, these would be the actual token IDs of the input, right? So I'm just having some sample here to play around with. And then what we can do is we can call this on our batch, and hopefully it generates the correct tensor. And we can see, yeah, so everything has the same length. Now we have padded the other ones so that everything has the same length. So that is essentially what our first draft of the collate function is doing. The next step will be creating the target IDs here. So for that, I could technically just copy this, maybe call that draft 2, and then I create maybe targets list here. Let me see what else. Yeah, here down here we will be also including the targets, and the targets are shifted by 1 position. So if I do targets torch tensor, oops, padded, and then there should be a parenthesis, of course. And then we are truncating. Oh, so we are essentially removing the first item from the input, which will mean that we are shifting everything over by 1 token. And then we keep collecting them in our list, targets. And then I think here we should probably also return those. Might be a good idea, right? Otherwise we do all the work and it is for nothing. Just double checking. I wrote targets as a plural, making sure everything looks okay. Okay, so there we go. So yeah, we mentioned returning, so let's not forget this. So now we have our draft 2. Let's see if that works. So shouldn't be append here. There we go. So now we have our, I mean, it's a bit hard to read. So we have the input and the target. So let's maybe also call or make 2 variables, and then it might be easier to read. So let's just do this. Let's look at the inputs first. So the inputs are the same inputs that we had before, ideally, because we didn't really change anything. We just added the targets, right? And so the targets are now shifted by 1 position. So instead of 0, 1, 2, you can see it's 1, 2, 3. So yeah, so that's it. So we have now created the target list. And the next step will be finally the masking, and that should be our last step in the collate function that we need. So then let's just call that custom collate here. And yeah, there are a few new parts I'm going to add. So first, what we need is, let's say, the ignore index. So for the ignore index, I'm using -100 because that's the default value that the cross entropy loss will ignore. Or we could use a different number and we can then change it in the cross entropy loss if we wanted to. So you can choose 99 or -1, but you just have to then make sure you update also the cross entropy loss. Personally, I just find it easier and more intuitive to just use the -100, which is the default ignored value in the cross entropy loss. And then let's also add a allowed max length to truncate in case we have inputs that are exceeding the context length that our model supports. So first, let me add the code for modifying the targets for with a mask token. So here, what I'm doing is I'm replacing all the target padding tokens by the -100, except one of them. We keep one of them because we want to teach the model when to stop generating text. So this one will be used to teach the model, okay, this is the stopping point. So then in the generate function that we have, we can check if end of sequence token is 50,256, or so if the current token we are generating is the end of sequence token, which is 50,256, then stop generating. And that is why we want to have it in here. The other ones we can ignore, like I mentioned. So here, that's what we are doing. So we create this mask. We check if a given token ID is a padding token ID. And then for each, but the first one, we insert this -100 here. And that is one thing we do. The other thing I mentioned is we are also truncating to make sure that none of the tokens have more, so none of the training examples have more tokens than our context length of the LLM supports. So here we are just truncating by the longest sequence. This is really similar to what we have done before. And I hope this works. So I hope I didn't make a mistake. So if this works, let's just use this example again and see what we get. So we call it now custom collate. Call it in the batch, and then let's look at the inputs tensor. Looks exactly still like it looked like before, which is desired, right? We didn't change the inputs, but the targets, they should now contain our -100. So we can see everything but the first padding token got replaced with a -100, and that one will get ignored in the cross entropy loss. So before I end this video, let me briefly show you what I mean by that, because maybe you are a bit confused by that. What is happening? Why -100? What is this magic number? So I have a simple example here. So this is just so that we don't have to run the model, which we haven't loaded yet. I just have two training examples. So one example, just 2 token IDs, another example, 2 token IDs, and sorry, these are the one token ID with, so it's basically just a simple training example. Don't even think about it in terms of token IDs. Just think of it as the logits that the model outputs for the first training example. It could be similar to chapter 6, where this is the logit vector corresponding to the last token ID. I just want to illustrate something in the cross entropy loss here. So we have labels. Think of it similar to chapter 6. We have labeled 0 and 1, for example, and then we compute a certain value here. What the value is, it doesn't really matter. What I wanted to show you now is if I add a new entry here, so just copy pasted that. If I add a new entry, let me do it like this. A third entry, and let's do minus 0.6 and 1.7 or something like that. Well, 1.6, I just typed it. It doesn't really matter, and let's give it also we need the target, right? Let's name this 2 so it's not overwriting our first example. And so what we'll get is a different number. Makes sense because we have added a new training example. When we compute the loss, it will probably be different from this loss. We have now 3 training examples. And I wanted to show you now the -100 illustration here. So let's increment this again so we're not overwriting this. So what will happen if I now replace this by -100. So if I replace this with -100, you will see this value is exactly like this value, because now the -100 tells the cross entropy loss, ignore this one. So that's just like a little trick that we can use to ignore certain token IDs. And here we apply this trick to ignore these excessive amounts of padding so that the model training is not influenced by these excessive amounts of padding tokens. So it's as if we didn't have any padding tokens. Padding tokens are still there because we need to make sure everything has the same length, but they won't influence the training. And so with that, we now have, we have explained how we batch the data. In the next section, we will talk about preparing the data loader.
Get this book at manning.com